Welcome back to Chapter 5. Today we're going to be looking at Section 3, which is about sum and difference identities. Now these identities are a little bit different than the ones that we've looked at before, but we're going to be looking at how we can add and subtract different angles inside of our trig functions. So we'll have like sine of x plus y type things and how we can deal with that. So our learning targets, we're going to use sum or difference identities to find the exact value. We're going to rewrite a trigonometric expression in terms of a single trigonometric function. We're going to prove trigonometric identities using sum and difference identities, match graphs with pairs of equations, and solve trigonometric equations. So the cosine of a sum or difference, the very first thing is that sine, and I was going with cosine of x plus y does not equal cosine x plus cosine y. The same thing is true with sine. You cannot add them together. If you think about it, the cosine has to be in between -1 and 1. Well, if you added two of them together, you could get something above 1, so it wouldn't possibly even work or make sense. So you cannot just add them together. There is a formula on how to do that. For cosine, it's the cosine of u plus or minus v. It's basically the same for addition and subtraction. Is cosine u cosine v minus sine u sine v. Now notice the signs here and here are flipped. That's because when you are adding, you subtract, and when you're subtracting, you add. So the sign has to change in with both of them. So if we wanted something like the cosine, to find the cosine of 15, to find the exact value of the cosine of 15, we don't know the exact value. We have 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and then the different versions of those. We can use addition and subtraction to find a couple more. Now, not too many more, really only the 15s, because if we, of the ones that we know, if we add 30s together, or 30s and 60s together, we're going to get another 30 or 60, or 90 or 180. If we add 45s together, we're going to get 45s and 90s and 180s. And so the only way to get something new is to use a 45 and a 30 or a 60. So for instance, 15 degrees could be written as cosine of 45 degrees minus 30 degrees. When we're looking at radians, they're going to be the pi over 12s. So now we can use this, we can split it up using our formula. So it's going to be the subtraction one, so we'll be adding, so we'll have cosine of 45 cosine 30 plus sine of 45 sine of 30. Now we go back to that unit circle. Cosine of 45 degrees is root 2 over 2. Cosine of 30 is root 3 over 2. Plus sine of 45 is root 2 over 2. Sine of 30 is 1/2. We can multiply the roots. That gives us root 6 over 4 plus root 2 over 4. We could combine those into one fraction if we want. They do have common denominators, but we do not need to do that necessarily. But this root 6 over 4 and root 2 over 4, being that you're always using a 45 and either a 30 or a 60 when you're finding these exact values, these will consistently be the answer. There's really 4 choices. There's the root 6 over 4 plus root 2 over 4, root 6 over 4 minus root 2 over 4, and then flip them around, root 2 over 4 plus root 6 over 4, and root 2 over 4 minus root 6 over 4. And so we can find those exact values. If we wanted to write it as one fraction, it would be root 6 plus root 2 over 4. You can't combine those roots. All right. We can also use it to prove stuff. We can prove those cofunction identities. Cosine of pi over 2 minus x equals sine of x. Well, how do we know that? We can do these. So this is subtraction again. So we will add. So we'll have cosine of pi over 2 cosine x plus sine pi over 2 sine x. Cosine of pi over 2 is just 0. Plus sine pi over 2 is 1. Well, 0 times cosine is 0. 1 times sine x is sine x equals sine x. And we can prove that cofunction identity, that the that phase shift, the vertical or the horizontal translation, getting us the same thing. So that's cosine. So cosine of u plus v is cosine u cosine v minus sine u sine v. We have cosine times cosine minus sine times sine. The sine of a sum or difference, we have sine u cosine v plus cosine u sine v. In this case, the sign, the plus or minus, does not change. So if we have sine of 75 degrees, we could rewrite that. 75, it's going to be 45 degrees plus something, so 30. So that'll be sine of 45 cosine 30. Then we're adding, so we're going to keep adding. Cosine 45 degrees sine 30. And then we just go back to that unit circle. So sine of 45 is root 2 over 2. Cosine 30 is root 3 over 2. Plus cosine 45 is root 2 over 2. Sine of 30 is 1/2. We can multiply. Root 6 over 4 plus root 2 over 4. Add those together to get root 6 plus root 2 over 4. I would point out that, hey, notice these are the same thing, except that the sine of 75 and the cosine of 15 that we did on the last slide are actually the same thing. So, but we could do it with, we could do it in radians as well. So pi over 12. When you're finding these, I'd always start out with a pi over 4. Because it's going to be a pi over 4 and a pi over 3 or a pi over 6. So we need to make it with a denominator of 12, so that'll be 3 pi over 12. Well, to get 1 pi over 12, we'd have to subtract 2 pi over 12, which is pi over 6. And so now we have subtraction, so we're going to subtract. So we're going to go sine of pi over 4, cosine of pi over 6, minus cosine pi over 4, sine pi over 6. So the sine of pi over 4 is root 2 over 2. And this is, again, unit circle just with radians. Cosine of pi over 6 is root 3 over 2. Minus cosine pi over 4 is root 2 over 2. Sine pi over 6 is 1/2. And you might be thinking like, wait, that's the same thing we just did for 75. This would be 15 degrees. Well, it is basically the same, but notice that we were subtracting now instead of adding. That's the difference. Remember, I said that these numbers are all going to end up being the same. We have root 6 over 4 minus root 2 over 4, which is root 6 minus root 2 over 4. So these sum and difference formulas are really just plug it into the formula and then take it to the unit circle and crunch, just do the little bit of multiplication. You're always going to end up with the same numbers, just might be plus, might be minus, and the root 2 and the root 6 might switch places. And that's when you're finding the exact values. Sometimes we can go the other way too. So write each following as the sine or cosine of an angle. So here we have sine 22 degrees cosine 13 degrees plus cosine 22 sine 13. So we want to go backwards here. Well, which one of these had sine cosine plus sine cosine? That would be the sine. So this is the sine of, and then we add the angles, 22 plus 13, which would be the sine of 35 degrees. And that's all we have to do. We just write it as the sine or cosine of an angle. We don't have to figure out what it is. Here we have cosine times cosine plus sine times sine. That's going to be a cosine. And since we are adding here, that means we're going to subtract the angles. This means it's cosine of pi over 3 minus pi over 4, which we can make our common denominators. That's 4 pi over 12 minus 3 pi over 12, which would give us cosine of pi over 12. Or this one, we have sine times sine minus cosine times cosine. We don't have sine times sine minus cosine times cosine. We have cosine times cosine minus sine times sine. So that's the first thing we'd have to do. We could factor out a negative here to get cosine x cosine 2x minus sine x sine 2x. And now this looks like a cosine. We're subtracting, so we're going to add the 2. So that'll be negative cosine of x plus 2x, which is negative cosine of 3x. So we can use the formulas going both directions. The tangent of a sum or difference. So the tangent of u plus v, tangent is sine over cosine, so that's going to be sine of u plus v over cosine of u plus v, which we can use our formula. So sine of u plus v is sine u cosine v minus plus cosine u sine v over cosine u cosine v minus, because we do have to switch the sign on that one, sine u sine v. And then we can divide everything by cosines, and it simplifies kind of, depending on what you want to consider simplifying. It can be written as this way: tangent u plus or minus tangent v over 1 minus tangent v. So what happens is we would divide everything by that factor in the denominator. So we would end up with sine u cosine v over cosine u cosine v plus cosine u sine v over cosine u cosine v over, when we divide by itself it's 1, I'm just going to leave that, minus sine u sine v over cosine u cosine v, and then some stuff cancels. We had cosine u's here, we had cosine v's there, and then everything else forms tangent. We have tangent of u. This would be tangent of u. This would be tangent of v. This one would be tangent u times tangent v. This sign right here switches because it comes from cosine. So notice that this sign down here has switched because, again, from the cosine. So this one down here is the tangent. So I'm using tangents. Sometimes that doesn't work out so well, and having it written as sines and cosines is a lot easier. So you could use either of them depending on the situation and what you're given, but that's where this tangent formula comes from. It's just a sine over cosine, then simplified, kind of. And then writing is a single sinusoid. Last chapter, we were looking at the composition of functions, and sometimes we had two trig functions added together that made a sinusoid. Sometimes it didn't. And sinusoids are the ones that can be written just as a sine function. So we can actually do that now. Express 2 sine x plus 5 cosine x as a sinusoid in the form f of x equals a sine bx plus c. So the first thing we would want to do is we want to actually split this up because the function is split up. So using our sine addition, we have sine bx cosine c plus a cosine bx sine c. So notice that a distributed to both of them because it would have been parentheses. So we have f of x equals 2 sine x plus 5 cosine x. So the first thing we would want to do is we have a sine x plus cosine x. So here we could rewrite this f of x equals cosine c is just a constant. So this a cosine c is just a number. So we have sine of bx plus, then sine c is a number. So we have a sine c cosine of bx. Well, notice these are the same. If you remember, we could tell if it was going to be a sinusoid or not if that b value was the same for both of them, and it is. So in this case, b will equal 1. And then we need to figure out what the other ones equal. Well, 2 sine x is a cosine c of sine x, so 2 would have to equal a cosine c, and 5 would have to equal a sine c. And so we have two equations and two variables. So this is a system of equations, but it's not a system of equations like one that you would have seen in the past. To deal with this, the very first thing we're going to do is we're going to square each of these. And we can do that because if 2 equals a cosine c, that means that 2 squared would have to equal the square root of a cosine c. So 4 would equal a squared cosine squared c. And then 25 would equal a squared sine squared c. We did that. Now we're going to add these two functions together, or these two equations together, just like we do with elimination. However, we're not going to eliminate anything right off the bat. What we're going to have, I'm going to flip my order here, so we have a squared cosine squared c plus a squared sine squared c equals 4 plus 25. So it didn't cancel like usual. Usually we'd have like a 3x plus negative 3x, and the x goes away. But if we factor out this a squared, equals 29. So we're left with a squared times cosine squared c plus sine squared c, which Pythagorean identity equals 1. So there's where that variable cancels. It takes an extra step. Now, chances are that kind of came as a little bit of a surprise, like, oh wow, okay. I would not have expected you to just like do that off the bat, but this is the steps. When you're doing these problems, you want to square them, add them together. Pythagorean identity goes away, so we have a squared equals 29, which means a equals plus or minus the square root of 29. We're going to use a positive one and plug it into any of the two original ones. So we have 2 equals a root 29 cosine c. We can divide by the root 29, so we have 2 over root 29 equals cosine c. So c would equal the inverse cosine of 2 over root 29, which is just a value. It's, not going to be a pleasant value, but it is just a value. And then we could do the same thing for sine. 5 equals root 29 sine c, which means 5 over root 29 equals sine c. So c would be the inverse sine of 5 over root 29. So to check to see if it was positive or negative, we would want to make sure these two things are the same, and in fact they are. If one of them had the wrong sign, we'd switch it to negative, and that would hopefully fix that issue. So c equals either of these two things. So we can rewrite, we have f of x. So going back up to this equation, we know what a is. A is root 29 sine of b, which is just x, and then plus, we can pick either of the two. I'm going to go with cosine. Cosine inverse of 2 over root 29. So we just put those values back into that formula that we know it needs to look like, and that's what it is. Now in this case, I know it's easier to deal with the original than when we write it as 1, but the directions were expressed as 1, so that's what we do. So today we have the sum and difference of sines and cosines, tangents as well, and it's just, here's a couple formulas, here's the identities, and it's just using those. They are on your formula sheet, so don't be afraid to be looking at that, especially at the beginning. Hopefully after a little bit of practice, you don't need it quite as often for this, but it is still there for you. But I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.